Is this working? No. Now it's working. So while Serge is getting set up, I'll take the opportunity to do a little bit more of a formal introduction than I did for Dave. Just as Dave comes from the grand atomic physics tradition of Norman Ramsey, Serge comes from the grand atomic physics tradition of Claude Cohen-Tanucci and before that Alfred Kastler at the École Normale. So besides being at the École Normale, Serge is a professor at Collège de France, and of course shared with Dave the 1912 yeah the 2012 Nobel Prize in Physics.
So, like Dave, I would like to thank Gretchen and Trey for organizing this wonderful meeting in such a historical place. I knew it was a historical place, but I was impressed to learn that Roosevelt wrote his inaugural speech next to the suite I am staying in. So it's very impressive. And this is a speech in which he said that the only thing we have to fear is fear itself. And I think this is an advice which should be given to today's politicians in the worrisome time we are living. Yes, and physicists too, yes. Anyway, I think it's a great honor for me to talk in the same session as Dave, the first session of this ICAP meeting. And what I would like to do, as he did, is to review my own involvement in this kind of physics, give a kind of historical account of my work there, and also to give a brief report about the latest development in this physics at École Normale Supérieure and Collège de France in Paris. After Dave's talk, I think it's appropriate to stress the similarities between our experiments and the experiments that Dave has been doing in Boulder. In his case, they are trapping single atoms, single ions, and use laser beams to manipulate, control, and detect these ions. And in Paris, we do, so to speak, the opposite. We trap single photons in a high-Q cavity, and you use beam of atoms crossing the cavity to manipulate, control, and measure the properties, the quantum properties of the field. In both cases, in fact, so we are doing experiments which are the two sides of the same coin, so to speak. And in both cases, we are performing in vivo physics. That is, that we observe systems that we want to be able to manipulate without destroying them, which is rather difficult, specifically if you talk about photons. Of course, as Dave said, we are dealing, it's a game which is played by many groups in the world, and you will have many, many other talks in this conference dealing with this topic, especially in the case of cavity and circuit QED. You have many talks in the conference and posters this afternoon. What makes this experiment very similar is that we use the matter-light interaction at its most fundamental level. Basically, we have to understand how a single atom interacts with a single photon. Just to stress this similarity, I like to show two experimental signals which are taken from two papers published by our group and by the Boulder group. You see here the Rabi oscillation of a two-level atom while the atom is crossing a cavity which contains a small coherent field. And here you see the same kind of Rabi oscillation observed on a single ion, which is undergoing coherent motion in the trap. And you see that the two signals look very similar. You have a beating between different frequencies corresponding to the different Rabi frequencies assigned to different photon numbers. And when you take the Fourier transform of these signals, you get peaks which show the graininess of the photon field in our case and of the mechanical oscillator in the ion case. So these experiments are direct tests of harmonic oscillator quantization in two different contexts. Let us also note the date here. Both papers were published simultaneously in the same issue of PRL, and this illustrates what Dave said about this friendly competition between cavity QED and ion trap physics. I like also to show on that occasion this picture, which was taken at the same time of Dave and I in the Boboli Garden in Florence. And I must say the picture is not very good, the quality is not very good, but I'm almost more proud of this and of these signals because Claudine and I were able to lure Sedna and Dave out of physics. It was just after the Amsterdam ICAP conference, and we convinced them it was a good time to go to take some vacation in Italy. And I still remember Sedna saying, when we talked about the vacation, I think the concept does not exist for them. But still, we had a very good time, a few days in Tuscany. Of course, a lot of things happened since then, since this first signal which shows the quantization of the field in our cavity. And since I will not have the time to discuss in detail all the physics, I have summarized in the next 2 slides the main achievements that the ENS group was able to obtain during the following years. The most important result was the ability to count photons without destroying them, which is quite different from the usual detection of light, photodetection using the photoelectric effect, which destroys the photons. So in this way, we are able to observe the birth, the life, and death of single photons in the cavity to prepare Fock states of light, which are highly non-classical states, and to see the decay of the field step by step as observing the quantum jumps of the cavity field as the photons escape one by one from the cavity. And this kind of picture is quite different from the classical pictures in which the decay of a classical field is exponential instead of being a staircase process. We are also able to reconstruct non-classical states, such as Fock state, and to reconstruct the Wigner function, for instance. And also in a series of experiments, we are able to produce Schrödinger cat states of light, that is superposition of field state with opposite phases, and to reconstruct the Wigner function. You see here one component corresponding to a current field with a given phase, and then the field with the opposite phase, which symbolizes the live and dead cat, and in between, the fringes in the Wigner function, which shows that we have indeed a coherent superposition of these 2 states. And by taking snapshots of this kind of Wigner function at increasing times, we are able to observe the decoherence process and to demonstrate also the fragility of these states which decohere faster and faster when you increase the number of particles in the system. So these experiments have been performed during the last 10 or 15 years, and rather than giving a kind of didactic account of all this physics, I would like to take a more historical viewpoint and try to describe how we got into this kind of physics over the years. So this started during my PhD work, which was performed in the 1960s, and I had the great luck to start this research in a lab where very interesting ideas were being developed at that time. It was a time of optical pumping, and methods to manipulate atoms with optical beams were being developed, and these are, so to speak, the 4 fathers of all the techniques which have been developed since to manipulate matter with light. This picture was taken on the day where Kastler Nobel Prize announcement was made. So you see on this picture first Kastler and Brossel, who had invented optical pumping, and on the left you see Claude Cohen-Tanucci was a young student of them, and who had discovered the light shift effect, which is going to play a very important role in the following of my talk. And you see I'm here in between them. So Dave said that he was getting close to one boss, and you see I was able to get close to 2 or 3 bosses at the same time. And I was really thrilled to have fallen in a lab where such fantastic physics was being developed at that time. Claude assigned me an optical pumping experiment to do, and he gave me an experimental setup. I had a cell filled with mercury. In fact, the cell was prepared by Brossel, who was coating the walls of the cell so to protect the spins from relaxation for a very long time. And then I was using optical pumping with circularly polarized light to orient the spin, the nuclear spin of this mercury vapor in one direction. And the absorption of the cell was allowed us to measure the degree of polarization or degree of orientation of the atoms. And then I applied an RF oscillating field perpendicular to the axis of the laser, the optical beam, so as to flip the spins when a resonant condition was observed. And 1, 3, or 5 quanta of radio frequency field were absorbed. The spin flipped, and this changed the absorption signal, and I was able to record these resonances 1 quantum, 3 quanta, 5 quanta resonances. Also, I was able to see that there was a radiative shift when the radio frequency intensity was increased. This is a shift which is quite similar to a light shift effect, and in the context of RF spectroscopy, it's called the Bloch-Siegert shift, but it's the same kind of shift. So I am very fond of this picture because it's the first experimental signal I ever got in 1965. It's a spectrum observed in optically pumped mercury, and it already deals with the interaction of atoms with RF photons, which is going to be my topic of interest, has been my topic of interest since then. And it already uses light shifts and exploits light shifts. But of course, these are produced by zillions of photons, and of course, you could describe all these effects classically. Nevertheless, Claude and I discovered that it was very useful to use a full quantum picture and to describe this in a quantum way. And we developed the dressed atom formalism, which describes the atom plus field system as a combined system whose energy level give in a very synthetic way all the properties of the system. This was just a commodity for this kind of experiment, but this dressed atom picture became very useful later on, especially in our cavity QED work, when we go down to a single photon, and then, of course, we have to quantize the field. All these experiments were performed with classical lamps, and at the end of the beginning of the 70s, I decided it was useful to try to get some expertise with lasers, which were then being developed, and we understood at that time that there were going to be fantastic tools for atomic physics, and especially atomic and molecular spectroscopy. So I went to a place which was a mecca of this kind of physics at that time, the group of Art Shallow in Stanford, and Art was just starting to work with a young associate professor, Ted Hensch, coming from Germany. So this is a picture of them around that time. And this is where I learned to work with tunable lasers. I was performing there a quantum beat spectroscopy experiment, exciting with short laser pulses an atomic vapor, and looking at the modulation of the fluorescence light, which reveals the coherence of state superposition excited by the laser pulse. So I learned on that occasion the importance of this concept of state superposition in quantum physics. But most importantly, I learned to use these lasers, whose development led to really a revolution in atomic physics. At that time in Stanford, it was as exciting as in Paris. Almost every week, a new method for high resolution laser spectroscopy was invented by Ted and Art, and it was a very exciting and thrilling time. So after that, I came back to Paris, and my problem was what to do with this new tool. You see, here I am in my office in Paris with my first 2 graduate students, Michel Gross and Claude Fabre, and we're thinking about what we could do with these laser sources. And what we decided to do was to study very excited Rydberg atoms. These atoms, of course, had been known at that time for almost a century. It was known that there was a lot of very excited states very close to the ionization limit, but they were impossible to excite in the lab with classical spectral lamp, which did not have enough intensity and enough selectivity in frequency. So we understood that using lasers, a kind of terra incognita involving a huge number of states became available, and we decided to study them with other, of course, other people at the same time in other labs started also this kind of study. A few years later, when I was asked to write a kind of popular account of this physics in La Recherche, I drew this kind of artistic view of the 30s state of hydrogen. It was a time where we were not yet used to employ computers to draw wave functions, so I just did it by hand. And just the idea was to show the huge size of these atoms compared to a ground state atom or to even a DNA molecule here, which is really dwarfed at this size. And I wanted to say that this atom was the size of a biological object, a virus. And these kind of fluffy and big atoms should be very sensitive because they were very weakly bound to all kinds of perturbations, electric and magnetic fields, and also radio frequency fields, which were exciting transition between nearby levels. So we decided to study these atoms, and the way to excite them with laser is well known. We use a stepwise process. The first laser excites the resonance transition, and then with another level or a couple of other levels, we get very close to the ionization limit into Rydberg states. And then once you are in Rydberg states, you can use microwave transitions to explore higher and higher angular momentum states, and we did a lot of studies of that time at the end of the 1970s. And if you look at this manifold of states close to the annihilation limit and increase the angular momentum, you reach the highest possible angular momentum state, which is called the circular state. And this state is just an electron going around on a circle around the nucleus, and this is a realization of the old Bohr model of the atom of 1913. And I was really fascinated by this physics, not only because these atoms were were supposed to be very sensitive probes of their environment, and there was a lot of hope to be able to do very interesting experiments, but also because these were very simple systems. We did not need to use a lot of sophisticated quantum physics to understand the behavior. In fact, classical physics was enough, just adding one quantum concept. For instance, here you just have to say that you need to have an integer number of de Broglie waves around the orbit just to find the Rydberg formula. So it's a system which looks very much like hydrogen, scaling as a square, with size scales as a square of the principal quantum number. They have very long lifetime. They are extremely sensitive to everything, and also to interaction with other atoms through a huge van der Waals interaction. So I just want to stress that we have used them since the 1980s in our ENS work, but the interaction between the Rydberg atoms is now being exploited in a lot of very beautiful experiments, other kind of quantum physics studies involving quantum information, for instance, which exploits the huge van der Waals interaction between atoms. And as now we are able to control the position of cold atoms with very high precision, these experiments are really blossoming, and you have many examples of that in this conference, oral and presentation and posters. But we use this essentially in our experiments, these circular atoms, and I want to say a few more things about them. So to prepare an atom into a circular state, you start from the ground state, and using a rather complex preparation scheme using lasers and radiofrequency photons, you promote an electron in the circular orbit. I won't describe this method, which was pioneered by Dan Kleppner and Randy Hewlett at MIT in 1983, but we have been using variants of this excitation scheme to prepare on-demand single circular atoms. As you see on this orbit, the electron is fully delocalized, so you don't have an electric dipole on the atom. If you need an electric dipole, what you can do is to use a microwave pulse which admixes two states of two adjacent Rydberg states, whose principal quantum number differs by 1 unit. In this case, and again, it's a kind of classical interference process, the two de Broglie waves interfere positively on one end of the orbit and negatively on the other end, and you get an electric dipole. And this dipole is rotating at the frequency, which is here 50 gigahertz. So you can look at this localized wave packet as the clock hand on a dial. And in fact, this picture of an atomic clock, Rydberg atomic clock, will be very useful to explain all our experiments. So what are the questions that we tried to answer with these giant atoms back in the 1980s? One question is, will it be possible to use their huge sensitivity to radiation in order to observe the interaction of single atom with single photons? And this was really the route towards cavity quantum electrodynamics. The second question is, can we use Rydberg atoms in order to detect single photons without destroying them, using the high sensitivity of these atoms to use dispersive effects to observe photons one by one? And the last series of questions, can we use them to manipulate quantum fields and prepare them in quantum states, presenting counterintuitive properties like Schrödinger cat states of radiation? I must mention that in order to do that, as we will see, there is a great advantage of isolating the system into a high Q cavity and to go into the system, to study system in which Rydberg atoms interact with photons in a high Q resonator. At the time we were asking this question, we were competing with the group of Herbert Walter in Munich, who had developed his own version of cavity QED using Rydberg atom and microwaves. And he invented at that time the micromaser, which was a quantum device in which the quantum field was built in the cavity by the interaction of atoms crossing the cavity one by one. And the micromaser was, in fact, the topic of Dieter, thank you, of Dieter's PhD back at that time. Where is it? Okay. So it was a very exciting time, and we developed tools to perform these experiments, and after some time we end up with a setup which I try to show on this slide here. Our cavity was made of two highly polished mirrors covered by a thin layer of niobium. They were superconducting mirrors, and light was bouncing a huge number of times between the mirrors, more than 1 billion bounces, and the photons were trapped in this cavity for more than 1/10 of a second. Atoms were crossing the cavity one by one. Each atom was a circular Rydberg atom, and you see each atom was interacting with the cavity for about 20 microseconds. So we could send thousands of atoms one by one before the field decayed in the cavity. And in this way, to prepare this very strange quantum state and study how they behaved. And in fact, when we did this experiment, we realized that they were rather close to the thought experiments of the famous photon box experiments that Einstein and Bohr discussed at the Solvay meeting in the 1920s. You see, their box did not look quite the same as our experiment, but you had the same ingredients. Of course, the box is our cavity, and the clock, which is used to time the escape of photons from the cavity, was just our Rydberg atom, which we would use as a Rydberg atomic clock. So I have here a few pictures which were taken at that time when we were discussing these early ideas about cavity QED. You see, I am here with Jean-Michel Raymond, who was my third graduate student and was very lucky to be able to keep working in my group since then, and it has been a very, very fruitful collaboration. I will come back to that later on. And I was also discussing with friends and colleagues, and you see here a picture taken at Les Ouches Summer School in 1982, where I was discussing with Dave Klepner, and you have a lot of formulas about the various regimes of cavity QED on the blackboard. And I want also to acknowledge the great contribution of Philippe Gouat. Philippe Gouat was really a wizard of microwave technology, and he was working in the solid state group at that time, and I could get him interested in our experiment, and you see him here with the microwave equipment he was using at that time, and his microwave expertise has been very, very important for the development of our experiment at that time. So it has been a very long story, and I just want to describe here an early experiment in which we explored microwave transitions between Rydberg states. What we did was to excite an atomic beam with lasers so as to prepare them into a initial Rydberg state, and we applied microwaves in a small cavity made of copper just to define precisely the regional space where the microwave was irradiating on the atoms. And when the atom left the cavities, they drifted in these condensers, between these condenser plates, and to which we applied a ramp of electric field which reached the threshold for ionization of the Rydberg levels, upper and lower state of the transition at different times. This selective method, which was also pioneered by Dan Klepner, is very efficient and allows us to discriminate Rydberg states with high sensitivity and high yield. And this is what we saw when we looked, for instance, at the transition between the 27S and 26P level in sodium, I think. You see that we do not even have to apply microwave. If we start with the atom in the upper state, and if we tune the cavity in resonance with the transition between these two states, we observe a fast transfer of the atom from the 27X to the 26P state, which is spontaneous, which does not need any applied microwave. Philippe Gouat did not like that because his microwave system became useless at that point, but it was, in fact, the observation of a maser. The system was mazing, but what was amazing is that it was mazing with only 200 atoms at a time in the cavity, and this is, of course, because of the very huge sensitivity of the system. So in the conclusion of the paper, we wrote that we could go to very small absolute atom numbers. And this was really the start of our hunt for the cavity QED system, in which you have a single atom interacting with a single photon in the cavity. But our cavity was not good enough. It was just copper mirrors, and we had to improve on that. This is about the time where I gave my first talk in an ICAP meeting. It was an ICAP meeting which took place in Boston, and Frank Pekin and Dan Klepner was the chairman of this conference, and I gave a talk about Rydberg atoms and radiation, in which I tried to explain why these were useful systems to study fundamental radiative effects. And I showed in this paper one Rydberg atom maser signal. So in order to improve on this system, we went to superconducting cavities. And this increased the Q factor in such a way that we reached very quickly the regime in which single clicks in our detector mentioning the fact that we had only one atom at a time in the system manifested this fast transfer from the upper to the lower state. So this was the limit of a maser with a single atom in the cavity. And it was also the first observation of the Purcell effect predicted in 1946, the enhancement of spontaneous emission due to the coupling of the atom with cavities. In fact, I was lucky to be able to discuss that when I visited Harvard in 1981 with Ed Purcell, who was very, very nice, very gentleman who was ready to discuss his ideas. And in fact, he told me that it was rather embarrassing for him because he published this idea of the Purcell effect as a small note in the proceeding of an APS meeting of 1946 following the paper in which he described NMR for the first time. And Isidore Rabi met him in a lobby of the conference and told him, you should be ashamed to write about this when you have written a paper about NMR. This is just something which is not relevant and should not be published. But everybody is now quoting the Purcell effect all over the world. So you see that Rabi had some ideas which were not very premonitory or prophetic. It's also, of course, a transient maser with a single atom. But we are not quite satisfied yet because the photon which was emitted in this cavity escaped very quickly because of the fact that the damping time of the cavity was not quite good enough. So in the end of the paper, we said that with a tenfold increase in Q, we could reach the regime in which the single photon could be kept in the cavity long enough to be reabsorbed by the same atom. And this was what is now known as the strong coupling regime of cavity QED. So this became our holy grail in the early 1980s. How can we reach this regime with an open cavity? And I illustrate this, why it was interesting for, why we found it fascinating to get into this regime. Assume that you start with an atom in the excited state with 0 photon in the cavity. After some time, the atom goes to the lower state and emits 1 photon. But if this photon can stay long enough, it can be absorbed. And now we have a 2-level system. And this is called the vacuum Rabi oscillation. And if you stop, in fact, if you look at the evolution of the wave function of the atom cavity system, it's a linear superposition of the state E0 and G1 with amplitude, which has a cosine sine of the Rabi frequency time t. And if you are able to interrupt this process and to have the atom leaving the cavity when omega t is equal to pi/2, you get a non-local entanglement between the atom and the cavity field. And so we had this idea of entanglement back in the beginning of the 1980s, but it took us a lot of time to get cavities good enough to be able to observe it. Eventually, we were able to observe this kind of vacuum Rabi oscillation. You see here a signal taken in the 1990s, excuse me. So you start with an atom in the excited state and 0 photon. If you perform a pi/2 pulse, you get atom-photon entanglement. If you go to a pi pulse, you go from E0 to G1, and you generate on demand a single photon in the cavity. And we have done many experiments of this kind. You can use this kind of system to demonstrate quantum gates and make simple quantum operation demonstrations. Now, of course, the question that we immediately ask, is it possible, once you have prepared a photon, to detect it and to have it in the cavity and to see it without destroying it? And this brings me to this idea of the QND detection. For that, we use a light shift effect, which was, as I said, discovered by Claude during his thesis work. if a non-resonant atom crosses the cavity, it undergoes a light shift which takes opposite sign for the atom in the state E and in state G. So it means that if you prepare a state superposition before the atom enters the cavity, this state superposition will accumulate a phase shift which will be proportional to the photon number. And because of the huge coupling of the Rydberg atom to radiation, the phase shift per photon phi naught can be very large, of the order of pi. So this means that if you have, whether you have 0 or 1 photon in the cavity, this state superposition will have opposite phases. And if you're able to detect this phase, we'll count the photons, 0, 1 photon, and without destroying it because it's a non-resonant process. Of course, to measure delta phi requires an atomic interferometer, and so this brought us to this, using the Ramsey setup, the atomic clock setup to detect the photons. So this is our setup here. It's a Ramsey interferometer. This is a box where the circular states are prepared. They drift along. They are detected here by field ionization. And the two important ingredients here are the auxiliary cavities R1 and R2, which are sandwiching the cavity in which we have the photons that we want to detect. And we apply a pi/2 pulse here to prepare a state superposition and a second flash of microwave to detect how this superposition has evolved. This is a clock which is delayed by the photons which are trapped inside the clock, and the delay is about 10⁻⁷ per photon, which is a huge effect for an atomic clock, of course. So you have fringes with 0 photon, fringes with 1 photon, and a pi shift per photon means that the fringes are shifted by just half a fringe interval. So if you set up your fringes here, you see immediately that you will detect an atom in one state if there is 0 photon, in the other state if there is 1 photon, and you see that we can detect photons without destroying them in this way. If you want to detect larger photon numbers, what you have to do is first to prepare a field with larger photon number in the cavity. So you use a horn, send a pulse of microwave, photons are captured on the edge of the mirrors, and you get a coherent state with a superposition of photon numbers in the cavity. It has a Poisson distribution of the photon number. And then you switch off the source, and you see that you have about 1/10 of a second to perform experiments on this decaying field inside the cavity. So to do that, you send atoms one by one across the cavity, and you use this shift in the following way. You see here the fringes that you observe if there is 0 photon. These are the fringes that you would have with 1 photon. Here are the fringes with 2 photons, and if you set your Ramsey interferometer at this phase, you see that you will have different probabilities to detect the atoms depending upon the photon number. So if you are able to acquire statistics before the field decays, you will count the photon just by looking at the probability to get the atom in one state or in the other. And we use this process to count the photons. And you see here, as the number of atoms increases and as you get more and more information about the statistics, that the photon number can converge either towards 5 or towards 7, and you get an ideal measurement of the photon number in this way. You can ask yourself many questions at this point. Can we steer n towards a predetermined Fock state if you use quantum feedback, if you react on the system in real time? Can we reduce the quantum noise? You see that there is an inherent quantum noise because each detection event is random, and you have some quantum noise which makes the photon number uncertain up to a given time. You can also follow this over longer time intervals and observe, first of all, the collapse of the field, repeat the measurement and observe that you get the same result, and then see the quantum jumps of the field. This is just a single trajectory of the field observed in this way. What about the Schrödinger cat? In fact, a single photon shifts the atomic phase of an atom, and reciprocally, a single atom shifts the phase of the field. So if you can prepare, you inject a coherent field in the cavity, which has a well-defined amplitude and phase, and you send a single atom in the cavity, and in the first Ramsey zone, you prepare a state superposition. The upper state will shift the phase in one direction, the lower state will shift the phase in the opposite direction, and immediately you prepare in this way a superposition of field states with different phases. If you detect at this point the atom, you will project the field with one phase or the other. A trick can be played by having the atom crossing the second Ramsey zone. Then if you do that, you mix again the atomic state before detection, and this maintains the cat's ambiguity. So you see that the Ramsey interferometer is rather a very magic device, which not only allows you to do atomic clocks or to do high-resolution spectroscopy, but also to prepare ambiguous states, and then when you detect, you get a Schrödinger cat state. I want also to stress, because we are here at ICAP meetings, that all these results have been reported at ICAP. This is the 1994 meeting in Boulder, where Jean-Michel Raymond presented the method of atomic interferometry to do all this. And this we owe a lot to the collaboration with Luis Davidovich and Nissim Zaghuri, which we were working with us at that time. Then at the next ICAP meeting, I described the Schrödinger cat experiment. It was in Amsterdam in 1996. And then a few years later in Stores, I described in detail the quantum demolition photon counting and the reconstruction of non-classical state in the cavity. I would like to mention another ICAP meeting, the one which took place in Paris in 1988, because there we reported about the two-photon Rydberg atom micromaser, which is a system a little bit different from what I've discussed so far, but this was a PhD work of Michel Brune, who also stayed with us since that time. And in fact, with Jean-Michel and Michel, we are really working together in all these experiments. So now, in the remaining few minutes, I would like to say a few words about what we have been doing recently during the last 2 or 3 years. This is a group as it was in 2012 with Michel and Jean-Michel, and I want to stress two young colleagues working permanently in our group now, Sébastien Glaise and Igor Dotsenko, who are the leaders for the new experiments, quantum feedback, quantum xenodynamics, and past quantum state analysis. And if I have 5 minutes, I would like to say a few words about these 3 experiments. Quantum feedback first. What we want to do is to steer the field, not to let the field go randomly toward a given Fock state, but during the measurement to steer it towards a predetermined Fock state. So this is like juggling game. You know, you have to observe what's going on and to react on the system. Now, the difficulty is that when you observe a quantum system, you have a random back action on it, and you have to take into account this random back action to correct for it. And we use, of course, a computer which performs a QED measurement, estimates in real time the effect on the system before applying a correction. And the theory of this was done with Pierre Rouchon's team at École des Mines in Paris. So I just have on this slide to explain briefly what the back action due to single atom detection is. Here I have just written the probability to detect an atom in one state, E or G, provided you have n photons in the cavity. It's just the fringe function of the interferometer, whose phase depends upon the photon number. But this is not what we are really interested in. What we are interested in is the reciprocal probability. Not what happens if you have n photons, but what happens to the field when you detect an atom in state G. And this reciprocal probability is related to the other one by Bayes' law. In fact, you have to take the a priori probability and multiply it by this fringe function of the interferometer, and you get the new probability. You get the way your probability is updated by the measurement. So updating the probability at the detection of the number S atom is just starting from the previous probability and multiply it by this quantity, which is the fringe function of the interferometer. And you have also to take into account the fact that between two measurements, there is some dissipation that you know about. It's 2 minutes left? Okay. And the dissipation operator is a linear operator which describes the photon loss. So each time you make a measurement, you multiply the previous probability by this. And this is a periodic function of the photon number, so you decimate some photon numbers each time you perform a measurement. And a succession of such steps converge randomly towards Fock state. Now the question is, can we act on the field between atomic detections to make this deterministic? And in fact, we can do it by a slight modification of the setup. The signal which is obtained by field ionization is fed into a computer which estimates the new field state, computes its distance to the target, and send a correcting field in the cavity to correct, to minimize the distance to the target state. And so you have atoms going one by one. I don't have time to play the movie, but you can imagine how it's going on. You have a kind of feedback loop which allows you to get closer and closer to the target. And here I will play the movie which shows really what happens. In the experiment, you see we start with a coherent field which has a Poisson distribution. And here you see the density matrix of the initial field, which is the density matrix of a coherent field. And you will see what happens as atoms get detected one by one. You see that there is a lot of noise in the beginning, and then at some point, you get into the target state, which is a state with 2 photons in the cavity. And then the loops, the system starts to make corrections until a quantum jump occurs, and you lose a photon, so then the correction is applied again, and you restore the photon, and so on. So I don't have time to discuss that too much, but you will see what happens as time goes on. We are able to correct, and in a steady state, to have an average given photon number, and we are able, by variance of this, to stabilize up to 7 photons in our cavity. So this is a quantum jump experiment. Quantum Zeno effect I won't discuss because this would be discussed in the Sébastien Gray's poster. I just want to say that, remind you that when you observe continuously or repetitively a quantum system, you modify its coherent evolution. You can freeze the evolution of the system, and if you make a measurement which is less precise, if you decide, for instance, so this is this is an experiment in which we froze a field to the vacuum, prevented photons to enter in the cavity because of repetitive measurement which projects the field continuously back into the vacuum. But there is a variant of this experiment which is very interesting, which is not to measure, but to ask a more precise question. Does the field reach a given value? For instance, does the field reach the value corresponding to 6 photons? If you can ask this question repeatedly, you prevent the field from crossing this value. And in phase space, you have a circle out of which the field cannot go. And if you look at a simulation of what we expect in this time, what you find is that the field gets to the limit, is reflected with a phase change, and at the time of the phase change, you get a Schrödinger cat. So again, a Schrödinger cat state, and this is a new way to prepare and manipulate quantum states in the phase space. And Sébastien will describe an experiment we did recently on this, and this is an experimental Wigner function that he was able to obtain, and so he will talk about that. Now, I would like, if I have 1 or 2 extra minutes, and I'm sorry to give a bad example, I would like to talk about the last problem, which I think is very interesting, the past quantum state approach to field monitoring. And in fact, this idea was given to us by this paper by the group of Klaus Möllmer in Aarhus. You see, when you monitor a quantum system which is coupled to a reservoir, what you do is that you upgrade the density operator up to the time where you want to compute the system. So this is exactly what I have discussed up to now. Each time you make a measurement, you multiply the previous photon number distribution by a function which described by Bayes' law the effect of the back action, and you have to take into account also the irreversible evolution due to the dissipation between measurements. But this is just Bayes' law, but when you do that, you see you acquire information, you have quantum and classical noise, and you also have ambiguities due to the interferometric measurement. And interferometric measurement is periodic, so for instance, you cannot distinguish between 0 and 8 photons, between 8 and 16 photons, because you have fringes which are periodic in photon number. You can win and decrease these uncertainties by exploiting information which appears after this time t. If you keep measuring after time t, you see up to a given time, capital T, much later on in the future, you get information because what happens to the system at a later time depends upon the state of the system before. And so if you combine the information provided by the forward and the backward approach, you get what is called the past quantum state, which is a product of these 2 photon number distribution, and in this case, you decrease considerably the noise. I can give you just a classical metaphor. what the ordinary technique is doing is a journalist work. You just look at the system and you look at what happens to it and you get some information. But this is ambiguous. For instance, if you had a journalist during the storming of the Bastille, he could not know whether it was just a riot or a revolution. In fact, the king said it's a riot, and one of his ministers said, no, sire, this is a revolution. And we know it's a revolution now because we have made measurement later on, and which impacted on the past. So the past quantum state approach is a historian viewpoint. And we did that for our experiment. You see here the ordinary description of a decaying field with a lot of noise due to this ambiguity, due to the periodicity of the photon numbers. You see at the beginning, you don't know whether you have 18, 12, 18, 10, or 2 photons in the cavity and a lot of noise. And you see here also that the quantum jumps are very noisy. If you look at the backward trajectory, it's also very noisy. But if you make the product of the two, you get a much better signal. And if you look at the probability to have various photon numbers, you see the noise has been considerably reduced. And in another experiment, we observed what happens if you prepare just 1 photon in the cavity. You see in green just the forward analysis, in which you have a lot of noise. The backward analysis, you have a lot of noise too. And when you make the product of the two, you get a very smooth signal, and it's much closer to the actual time of the real jump, which occurs around time t equals 0. So it's a very useful, Klaus Möllmer and his colleagues have developed a very useful tool to decrease the noise in the analysis of the system, and this can be used, I think, in a lot of metrology applications. In my last ICAP talk, I showed that it was possible to generalize that to circuit QED, artificial atoms replacing Rydberg atoms, and I just show you here 2 examples of Schrödinger cats. I won't say more about that. Of course, the big question, which was also asked to Dave, is what kind of application will you have a Schrödinger cat computer, or what else could appear in the future? Dave started his talk by showing a very optimistic Time magazine cover about what was going in the future. I don't like Time magazine so much, but I like the New Yorker much better. And I will show you 2 cartoons to end up, which were shown in the 1940 New Yorker, and which are prophetic. One, of course, is known from everyone. It describes the oddness of quantum physics. You see the skier which is going at the same time on both sides of a tree, and I think it must get entangled with the tree in some way by doing that. But this is just very simple entanglement. What we want is to have massive entanglement with a lot of particles. And here you have another cartoon published the same year in the New Yorker, and you see no entanglement here. In fact, at that time, I think the word entanglement has a different meaning. We come back to Roosevelt, and Roosevelt wanted to entangle American politics with a mess which was going on in Europe at that time, and so the Republicans did not like that. But you see that if you want to entangle too big ensemble, it raises a lot of problems, and I think we have this kind of problems in the quantum world. So again, I will conclude here. I apologize for being too long, but I just want to stress again the long-term collaboration with my 2 colleagues, Jean-Michel Raymond and Michel Brune, and I have listed on the last slide all the collaborators, co-workers, students, and postdocs who have worked with us over all these years, and I'm very proud to notice that about 1/2 are not French, and they come from about 20 countries. And if some of you are interested in a postdoc in our lab in the coming years, I think we have the possibility to welcome you, and I thank you for your attention.
Thank you, Serge, for that exciting, if a little overly long talk. So if you raise your hand, the runners will come to you with microphones, and I particularly hope that people in the back will raise their hands, because it shouldn't just be questions from the front.
So I have a question on the genodynamics. So basically in genodynamics, one probe beam tries to protect the coherence of the system, and now when both rates are there, like this decaying of coherence and the probe rate which is trying to protect, can there be any kind of bistable state?
What happens in xenodynamics is that we keep measuring a boundary of the system. We keep asking the question, does the system reach the boundary or not? And by just asking this question, we prevent the system from reaching the boundary. We destroy all the coherences which are linked to the passage through the boundary. And so the system is reflected on the boundary. And during this reflection, coherences are created because the reflections involve a pi phase change of the system wave function. And so in the middle, you get a coherence between the two. And so in the papers that we have written, and we explain how we can use that to generate new kind of coherences and observe things. But it's not really protecting the coherence. It's creating coherences because you truncate the Hamiltonian of the system, basically.
Okay, thank you.
Okay.
So more questions? While you're thinking of those, I can't resist asking one. Remembering, of course, that all interpretations of quantum mechanics are equivalent in the sense that they give the same answers. As someone who has used explicitly a Bayesian approach, that is one in which additional information modifies your view of what the quantum state is, has this given you a warmer feeling about quantum Bayesianism as an interpretation of quantum mechanics?
No, I don't think so. In fact, in fact, the Bayesian approach works as when you have chosen a basis and make a measurement and neglect all the coherences between states. But if you want to reconstruct fully the quantum system with all kinds of coherences, I think the quantum issues are there and the quantum problems cannot be bypassed just by Bayesian argument. That's my feeling.
Yeah. So if there are no more questions, I would like first to thank all the both of the speakers from this this morning's session, and then there will be one more thing to say. But let's thank both Serge and Dave. So